Okay, here's question 2. You're given the equations of two circles, and you have to write down the center and the radius length of each circle. My hint for this question is that this here is the equation of a circle, which you can find on page 19 of the Formula and Tables book. And in this case, h and k are the coordinates of the center of the circle, and r is the radius length. Firstly, I'm just going to rearrange my equation so that I have my x squared and my x together, and I have my y squared and my y together. Now, this here is the x minus h squared from the equation of a circle. What I'm going to do is expand that out and see if we can use what we get at the end. When I do the expanding out, I get an x squared minus hx and a plus h squared. Clean that up and you get an x squared minus 2hx and a plus h squared. So what I have to do is compare what I have here with this bit up here. I have an x squared minus 6x, and I don't have any constant there which would correspond to the h squared. So what I have is a minus 6 though, which would correspond to the minus 2h, which means my h is 3. So my h squared is going to be 9, which means I need a plus 9 right here. So now I have a plus 9 here. I also went ahead and found out that my k was plus 5, so my k squared is plus 25. And the way I got this plus 9 and plus 25 here was I split up the 29 into a couple of different parts. So I took 9 out of there, which went there, so I'm left with 20. Now I needed 25, but I only had 20, so I had to add a 5 and then take away a 5. That's why I have a minus 5 here. And just to double check, it's no harm to just add these back up, so 9 plus 25 minus 5 should get you back to the 29 that we had here. The next step then is just to take this x squared minus 6x plus 9, factorize it into this form here. Do the same thing with the y squared, the y, and the 25, so you get y minus 5 squared. Next thing, I added 5 to both sides, so minus 5 plus 5 is 0, so that's gone. And you end up with a plus 5 on this side. Now, I could have just left that as plus 5 here, but the equation of a circle has that I have an r squared here. So I got this into this form here, so I can tell immediately now that my r is the square root of 5. It's not 5, it's the square root of 5. Lastly then, just to formalize my answer, see this here, I've got an x minus 3, so that's an x minus h, which means that 3 here is the same as my h, which is the x coordinate of the center of the circle. Same here, I can tell that 5 is the y coordinate of the center of the circle, so the center has coordinates 3, 5. I also mentioned a minute ago that the radius is the square root of 5, so I can just take that right from here and put it down, square root of 5. Now I have to do the same thing for the other circle. So again, I'm just rearranging it to get my x's together and my y's together. Secondly, in this case, minus 2 corresponds to minus 2h, which means my h is 1, so I'm looking for a 1 squared here, just a 1. And again, the same thing for my y's. So now I split the minus 43 into plus 1, minus 45, and just double check again that they add up to minus 43, which they do. Then I just factorize my x expression here, factorize my y expression. I add 45 to both sides, so the minus 45 plus 45 is 0, and I have plus 45 here, which I turn into the principal square root of 45 all squared. So that tells me that the center of the circle is at 1, 1, and the radius is the principal square root of 45. Part B then is to prove that these two circles are touching. So my hint is just to figure out the circumstances under which two circles will touch. Take for example these two circles with radius 1 and radius 2. If these two circles are really far away, then of course they're not going to touch. So if the distance between their centers is greater than the sum of these two radii, then the circles won't be touching. Scenario 2 then is when these two circles are just touching at a single point there. And in that case, the distance between their centers has to be equal to the sum of those two radii. The third scenario then is when the circles are brought even closer together, and then you start getting 2 points of contact between the two circles. And this is when the distance between their centers is less than the sum of those two radii. But that's not the end of the story, because if one circle is a bit smaller than the other, then it's still possible for the distance between their centers to be less than the sum of the two radii. But in this case you can see the two circles are not touching, so that means we have another qualifying factor on the distance between the two centers, that it has to be greater than or equal to the absolute value of one radius minus the other. And I only put in the absolute value just because we need to make sure this is a positive length. If you make sure that R2 is the larger of the two values, you pick them arbitrarily, then the absolute value doesn't really matter too much. So on with the question. First of all, I know the distance between their centers is given by this formula here. These are my two coordinates, the centers of those circles. So I just follow the maths through and I get 4 plus 16, which is equal to the principal square root of 20. Now it's only with a bit of foresight that I clean this up, so rather than the principal square root of 20, I call that square root of 4 times 5. So that turns out to be 2 multiplied by the square root of 5. So I move on and I try and find the sum of the two radii, which is going to be the square root of 5 plus the square root of 45, which I got from part 1 of the question. So now I just follow the maths through and I get 5 plus the square root of 9 times 5. Again, I just want to get things in terms of this square root of 5 with a bit of foresight. So that turns out to be root 5 plus 3 times root 5. So in total I have 4 root 5s when I add them all up. So next then I work out the difference between the two radii, so it's root 45 minus root 5. Again, turn that root 45 into 3 root 5, which I had back here. And in total I've got 3 of something minus 1 of something, so I have 2 of something now at the end. I compare now these two values, the 4 root 5 and the 2 root 5, to my d, which back here was 2 root 5. Notice that it's actually equal to R2 minus R1. So if we go back to this diagram here, you can see that this here was exactly that scenario when the two circles are touching at exactly one point. D is equal to the difference between the two radii. So then D, the distance between the two centers, fits our qualifying factors exactly. It's greater than or equal to the difference between the two radii, and it's less than or equal to the sum of the two radii. Therefore, the circles are touching. And don't forget to write down that last statement. The question is to prove that the circles are touching. Here is your proof, and they need to know that you can actually conclude this statement from your results. Part C then is just to verify that this point is the point that they have in common. In other words, this is where the two circles intersect. And my hint is just to think about how can you verify if a point is on a circle. So all I'm going to do is verify that this point 4, 7 is actually on both circles. So to verify that it's on C1, I'm going to replace x and y with 4 and 7. So just follow that through. You get 1 squared plus 2 squared, which is equal to 5. And since 5 is the square of the radius of this circle, that means that 4, 7 is on the circle C1. So I do exactly the same thing with the other circle. This is the left side of the equation of the circle. I replace x with 4 and y with 7. So I just follow that through and I get 3 squared plus 6 squared, which is equal to 45. 45 being the square of the radius, that means that 4, 7 is on the circle C2. So 4, 7 is on each of the two circles, therefore 4, 7 is common to both circles. Part D then is to find the equation of the common tangent. Now if this is our situation here, where the circles touch a single point and one is inside the other, the common tangent is this line here that passes through that common point that they have, in this case 4, 7. Now if you want, you can use this equation here that's on page 19 of the Formula and Tables book. That gives you the tangent at this point 4, 7 for a given circle, and h and k being the center of whatever circle you're picking, and x1, y1 being the coordinates of that point you're looking at, in this case 4, 7. That method is a little bit on the trivial side though, so you should be able to work through that easy enough on your own. So I'm going to show you a different method that will work just as well, and it may even work in other questions of a similar style. My first step is to find the slope of the radius of the circle, that being this line here. That's the radius I'm talking about that goes to that particular point. So it's going to be 5 minus 1 over 3 minus 1, which is 4 over 2, which is 2. From there I can find the slope of this tangent being perpendicular to that radius. What I do is I take this 2, invert it, so it becomes 1 over 2, and change the sign. So I get minus 1 over 2. That's the slope of the tangent. So knowing the slope of that line and knowing the point through which the line passes, I can just use this general equation of the line formula that you get on page 18 of your formula and tables book. So I input my values, my y1 being 7, the slope being minus a half, and x1 being 4. Follow the maths through, nothing particularly difficult there, and I get y is equal to minus a half x plus 9.